So welcome again to our monthly Quantum BC seminar series. Today's speaker is Dr. Benjamin Crockett. Benjamin is a Banting postdoctoral fellow at the University of British Columbia, and he's working in the groups of Professors Lucas Krastowski and Jeff Young. His research focuses on generating novel entanglement quantum states on integrated photonic platforms for applications in telecommunications, sensing, and computing. He completed his graduate studies at the Institut National de la Recherche Scientifique, or INRS, in Montreal with Professor Jose Azaña. There he was developing photonic signal processing strategies for noise mitigation and time frequency characterization of classical and quantum systems. He received his Master of Science in 2019 and his PhD in 2025 on phase-based photonic signal processing for quantum state manipulation and analysis. So I'd like to welcome him today in giving his seminar on coherent energy redistribution methods for time frequency manipulation of classical and quantum photonic waves. So everyone, please join me in welcoming Dr. Benjamin Crockett. Thank you for being here.
About the research I've conducted. So when we prepare such a presentation, we want to think of a title that's somehow informative and catchy, and I think this one is a bit of neither, so I'll go in either extreme. So we could go even more wordy than what it is now and try to explain what each part means. So the coherent energy redistribution part actually means that we'll be using phase-only signal processing to maintain the energy of the input wave. And this is done to manipulate the information that's encoded in the time and/or frequency degrees of freedom. And this is done in both classical and optical quantum systems. But this would be even more of a mouthful. So I could go on the other extreme and go for the shortest title, which would be something like phase-based photonic signal processing. And still we would wonder, well, what is this? So I'm going to start from basic. What do I mean by this? And at the very foundation, we want to know what is photonic signal processing. So photonic signal processing is concerned with the synthesis, manipulation, and analysis of information that's encoded on a light wave. So for example, we could encode information either in the amplitude of a light wave. So we can turn on the light or off to signify a bit of 1 or 0, or alternatively, or in addition, we could encode the data into the phase of the wave. So you can see here that we have some kind of discontinuity in the carrier, which signifies that we have a phase shift, which we can assign as 0 or 1. And actually, by using both of these methodologies, we can have many levels in the intensity and many different phase shifts, which is the basis of encoding that is used for what is called quadrature amplitude modulation, which is often used in telecommunication. Alternatively, we could encode information in the amplitude or in the phase, but this time in the frequency domain. So for instance, we could think of some scenario for spectroscopy where the amplitude and phase variation may have some information about some material that we want to detect. And so from a maybe purely engineering point of view, we may wonder, when is it relevant to use photonic signal processing? Well, then we should have an advantage either in the processing speed, in the energy efficiency, or in the form factor of the processing scheme that we're trying to implement. However, there's a lot of important functional cases where photonic signal processing is just absolutely needed, either because we are dealing with signals that are very broadband and fast that cannot be dealt with by other means, or we have some scenarios, for example, in quantum optics, where we cannot digitize the information for processing. And out of these photonic signal processing strategies, there's a subclass of them that we would be called, this is the phase-only part, which means that we avoid discarding any of the signal's energy. So we would not use something like a temporal intensity modulator, and we would only be using the phase modulator to encode the information. And now, if we want to actually be having, so as we well know, if we do a phase manipulation in some domain, so for example, temporal phase modulation, this will not affect the intensity of the temporal wave. So if we want to do some intensity variation in the domain where we're modulating, we actually need to combine both temporal and spectral phase modulation. And this is the coherent energy redistribution part, where we are not discarding energy around, we're just focusing it in different areas to accomplish certain functionality. And so ideally, these are very interesting methods for processing signal because they are inherently very energy efficient, and they allow for very high speed processing. And so if you're interested in these topics, I suggest that you go through this review article that we recently published. But there's a wide range of functionalities that have been shown using this approach. So for example, where there's been the demonstration of NOT gate using phase-only processing, which can have some interesting application for computing. There's been some demonstration of data compression for optical communication, some noise mitigation demonstration, and some application for real-time spectral measurement. And then there's also been a lot of interest from the quantum optics community due to the energy efficiency that I've mentioned for all these wide range of different functionalities that can be implemented with this method. So this is the outline of the talk that I'll give today. First, I'll go through a description of the phase manipulation that I'm talking about, so temporal and spectral phase manipulation in the classical domain. I will then show how these can be applied to the case of entangled pairs of photons. And I will show how we can exploit this for dispersion resilient quantum interferometry. Then I will show how we can combine temporal and spectral phase modulation to do what is called a temporal imaging system, which allows for noise mitigation of entangled photon pairs. And finally, I will also show how we can use this for dynamic spectral analysis of broadband signals. And then I will conclude my talk. So just before continuing, I wanted to just tell you that if you have any questions during the talk, please feel free to raise your hand or let me know during the presentation. You don't need to wait until the very end. All right. So the basic idea behind the space-time analogy, which is a good framework to understand these phase-only manipulation, is that what we're trying to do is to implement imaging systems that we would have in a spatial domain. So for example, how we do microscopes or telescopes, and we want to apply this into the time domain instead to process our waveforms. So this allows to implement many important functionalities that can be done with lens systems, such as magnification, compression, or Fourier transformation. The basic idea behind it is that there's a very close mathematical analogy in the physical effect that these both systems have. So if we think of a thin lens, this will impart a quadratically varying phase along the wavefront of our image. This is what causes our light rays to acquire a tilt. And while we can implement this in the time domain by using a quadratic temporal phase modulation, which we can implement by using an electro-optic phase modulator driven by an arbitrary waveform generator. And then for the diffractive part, so this is where we have the free space propagation, for example, that will allow for these rays to focus at the focal point. Well, we can do this in the temporal domain by using a dispersive line, for example, a linearly chirped fiber aggregating or a piece of optical fiber. So just to give a bit more detail about what we mean by temporal phase modulation, you can see here I have some optical carrier. And when it counters a phase shift, you can see that there's an idealized discontinuity in the phase. So really, when we're doing temporal phase modulation, we're exactly doing what it said. And the way that we can implement this is with these electro-optic phase modulators, as I've mentioned, which in this particular instance, they rely on the Pockels effect. So when you have this RF signal, it will cause a change in the index of refraction, which will cause a change in the phase of the wave that exits such a device. So when we're talking about a time lens now, we're talking about a particular phase modulation. In particular, as I mentioned, this should be a quadratic phase variation in the time domain. Now, through basic principles of Fourier optics, we know that if we take the derivative of the temporal phase, we're effectively looking at the instantaneous frequency. So by doing a quadratic phase modulation, we are linearly varying the instantaneous frequency of our signal. So to look at what this means in a more application case, we can look at this waveform here, which is a kind of a narrowband waveform. Here I'm showing its one-dimensional distribution, which can be summarized by this 2D time frequency plot. And we can see that it has a very very small range of frequencies that extend over a long time duration. And when it goes through this device, this will cause this will lead to the creation of new frequency components that depend on the steepness of our quadratic phase. So this, you can see that we're effectively tilting our waveform in this time frequency plane, where the angle corresponds to the strength of our lens. Now we can look at dispersive propagation. This can be implemented using either optical fiber or chirped gratings. And in this case, if we go again through our basic theory of Fourier optics, we will see that the derivative of the spectral phase corresponds to the group delay. So when we are applying a quadratically spectral phase variation, we are effectively giving a different amount of group delay to each of our different frequency components. So again, when we have a pulse that will propagate through such a medium, we see that all these different frequency components travel at different speeds, which leads to a broadening of our pulse. So we can again consider a pulse like a signal similar to the one that we did before, except that now we can see that we have a wide range of frequency components concentrated over a short time duration. So in other words, we have a pulse. So when it propagates through such a device, now this pulse will broaden over time, and we see that again we have a tilting, except that now this tilting is with respect to the other coordinate. And so now we see that both of these approaches are complementary to each other in the sense that they both cause a tilting in the time frequency plane, but from a different perspective or a different reference plane. So now we may wonder, well, how can we bring these manipulations onto the quantum domain? So this is what I will talk about in the next section. And in particular, I'll give a description that relies on the non-local dispersion cancellation effect. This is an effect that has been applied for a wide range of application. And here I'll show how we can use it to understand the effect of dispersion. And keep in mind that I will focus the discussion on dispersion, but as I've shown on the previous slide, both dispersion and time lensing are kind of complementary from each other. So you can kind of understand what a time lens would do on a photon pair by just inverting the variables in your mind. All right. So before talking into too many details of the effect of dispersion, I think it's worth to take a moment to talk about the way that we represent entangled photons in the time and frequency domain, right? So whereas in the classical domain, when we have a signal, we consider something that is a one-dimensional signal that has an amplitude in the phase value. When we think about a quantum entangled pair, we want to think instead about a two-dimensional distribution that relates the time and either the time of both photons. So if we look at the time of both photons, we have what we call the joint temporal intensity, and you can see that, for example, on this side of this pulse, this will be correlated with this side of the pulse on the other photon. So that's why we have this two-dimensional representation, and this can also take a complex value. So all this kind of reasoning that we have behind classical signal processing, we want to bring it now into a two-dimensional framework when we think about entangled photon pairs. And so similarly, we can also take the two-dimensional Fourier transform of this 2D distribution, including not just the intensity, but the amplitude and the phase. And this allows now to look at the correlation in the spectral domain. So now that we have both of these, often it's very handy to also look at the projections of them. So for example, if we look in the time domain here, by doing a projection along the diagonal here, we're effectively looking at the correlation of two photons as a function of the time difference between them. And now if we're considering the case of parametric down conversion, we know that when a pump is converted to the daughter photons, this happens in a sort of instantaneous moment. So we expect to have very tight correlation between the delay because they should be created at the same time. And indeed, we would find that if we have such a distribution, the relative difference between them would typically be very small. Whereas if we look at the sum of their arrival times, this could take a very broad distribution. Yes?
Just for two photon correlation, one frequency, let's say a signal, is correlated to all of the other frequencies in the ether, or is it one-to-one?
It's more so I guess so in the frequency domain, then we want to look at the joint spectral intensity, and so you can see this 2D distribution as a histogram. So for example, if you look at the red part of this pulse, you see that there's no distribution here. So if you have a red photon on your signal, you will see that you will never get a red photon on the idler because the histogram has value of 0 here, whereas it has a higher intensity for the blue components because this relies now on the nature of the photon generation. If we have a low signal, a low idler frequency, this will be related to a high frequency on the signal. And so this is why we have this anti-correlation that we can see here. And on the other hand, in time domain, we have the opposite because they have to be created at the same time. All right. So now, right, to understand what the effect of dispersion, we want to understand how does this distribution change when it goes through a dispersive medium. Well, this is where we can now talk about dispersion cancellation. And what happens, the way that dispersion cancellation happens is that you would have each photon that propagates through a dispersion of opposite sign. And when this happens, you can see that the photons themselves have broadened, right? So on the top and on the right here, I'm showing the marginal, which you can basically understand as the single photon distribution. Like if you were looking only at the signal, you would get basically this distribution. And you can see that indeed, these two have stretched significantly. But if you look at the delay between them, they have not stretched significantly. So they remain highly correlated. So the difference between the arrival times of the photons remain highly correlated, despite the fact that the single photon themselves are broadly broadened. So because the correlations are typically seen in the delay between them, because the photons appear at the same time, most of the research has focused on the correlation observed as a relative delay between the two photons. And what we wondered is, can there be some interesting correlations that can instead be observed in the sum of the arrival times? So this is usually not very looked at, because if you consider, for example, CW pumping, you could have the sum of both photons being created just extends through infinity. You usually want to look at the difference. So, but we wondered maybe there's something interesting that can be happening here. So if you go with opposite dispersion, this is the case of dispersion cancellation, you can see that this 2D distribution stretches along the diagonal. What we realize is that if you instead have your two photons that propagate through identical dispersion, this stretching will instead happen along the antidiagonal. And so if you have a pulsed excitation, there's actually interesting correlation that can be observed instead in the sum of arrival times. So just by looking at the sum of the time at which your photons arrive rather than the difference, we can see that there's some correlation that can be exploited. And so we wondered how we can benefit of this for an application. And the problem that we wanted to look at is for the case of time-bend entanglement. Yes?
Does it look like two nodes using instead of being frequency quarter? Let's say quadrature sum of difference. This is time sum of difference correlation. Because the two nodes squeezing, you don't have squeezing for each of those quadratures per se. We have sum of difference quadrature.
I'd have to see. I'm afraid I don't know enough about squeezing to put it in that context. So we can continue after. So time-bend entanglement is broadly used in telecommunication because it's has a long coherence time in fiber, when compared to, for example, polarization entanglement, where the polarization can easily get scrambled through a fiber network. And so in this case, you have two photons that are in a superposition of being in either the early or late time bin, and we will always find that the photons arrive in the same time bin, so with high correlation. So, however, this scheme is fragile against dispersion because you can see that there can be mode mixing between our two time bins after they disperse. So we wondered, could we use dispersion cancellation as a way to counteract the effect of dispersion by simply analyzing the photons in a different way? And unfortunately, it turns out that dispersion cancellation cannot be used for time-bend entanglement because the stretching happens along the diagonal. So you can see here that there's a mixing that happens between our two modes in this joint temporal distribution, and there's no way now to figure out these counts that we have here to which mode they belong. So what we realized, though, is if instead we have both photons that travel through the same dispersion as we would have in a normal fiber network, then both of these time modes actually stretch out along the antidiagonal. So we can see here that we don't have any mixing. And so we wanted to show how we could use this in a quantum interferometry setup. So just to review some basic, this is the idea behind the experiment that we want to do. We have our time-bend entangled state. We put a different relative phase between these two modes by using an electro-optic phase modulator that processes both photons at the same time. And then we make it travel through an interferometer that has a delay that is matched to our spacing of our time bit. And so we are left with this 5 modes distribution shown here. The way we can understand how we got this is by looking at all of the different combinations by which our signal idler photon can travel through interferometer. And if we combine all of them, we have this 7-peak distribution. And when we do quantum interference, we're basically looking at the interference between this biphoton possibility and this one, because there's no way to differentiate this mode from which path it comes from. So basically, when we're going to be changing the relative phase between our two time bins, we're going to see these interference fringe in the joint correlations between our photons. So you can see here that the center peak, so the single photon distributions themselves don't change. But if you look at the joint correlations, you see that there is this change in the center peak. And so we want to be able to have high enough visibility in order to certify Bell's inequality for entanglement verification. So this is the experimental setup that we use to demonstrate this. We have a mode lock laser with a bandwidth of 50 gigahertz that we send through our interferometer. So this is still the classical pulse. We then take this two pulse that we have, and we send it through an electro-optic phase modulator for the quantum interference measurement. We amplify and filter it before sending it to our nonlinear waveguide, which here is a silicon nitride spiral waveguide. We then use a notch filter to remove the pump. And then we use a linearly chirped Fourier grating to emulate the dispersion from a fiber network. So this would be, this is the dispersion equal to 2,200 picoseconds squared, which is equivalent to about 200 kilometers of propagation if we assume that our photons go to opposite nodes. And then we would be using another interferometer and a demultiplexer to do the projection. And here, for simplicity, we actually use the same interferometer for both quantum state preparation and projection by simply traveling in two different ways. And this allows to inherently stabilize our interferometric structure. And so this is the result of our experiment. So without any dispersion, we see that by looking at the difference of the arrival time, so doing a projection along the diagonal only on this side, on this single mode, we can see that we are indeed able to satisfy the Bell's inequality violation. However, in the case of dispersion, we can see that there's a lot of mixing going on here. And so if we use the difference of arrival times, we're no longer able to certify Bell's inequality. But if instead we look at the sum arrival time, so now we're doing a projection along this anti-diagonal, again focusing only on the center time bin, we can see that we're able to satisfy Bell's equality in both cases, which shows that by simply taking the same data and not changing the setup itself, but just changing the way that we analyze the correlations, we can do dispersion-resilient quantum interferometry. Yep.
It's the playwright. I'm wondering if you're reusing your power is very relevant. But if you have two devices counter-propagating, they have some cross-talking. How do you?
I mean, I think what happens more is that you'll have some noise that will happen, but the noise was, I mean, you can do temporal multiplexing. Make sure that your classical pulse are not aligned with your quantum pulse on the way back, and then this caused no problem.
So around scattering, you have very long fiber.
Yeah, so that's why the temporal multiplex, as long as your pulses don't arrive at the same time.
Oh, I see.
They're unsynchronized, so then you'll see a noise peak,
yeah,
but it will be decoupled from
dedicated the greater side.
Yeah. All right, and then finally we use this in a QKD link, and we showed that if you look here for the same amount of dispersion, by using the sum arrival times, we're able to increase the secret key rate, again, simply by analyzing our waveforms in a different way. All right. So now we've seen how entangled photons are affected by dispersive lines and how it can be used to improve the dispersion resilience in a quantum network. Now we're going to look at how we can combine both temporal phase modulation and spectral phase modulation to do an imaging system and that how we can use this to mitigate the effect of noise in quantum states. So in an idealized scenario, if we return to the case of time-bin entanglement, we would want to have only coincidences at zero delay. So we will always want that our signal and idler photons arrive at the same time. However, in a real scenario, what we would have is that we will have a whole bunch of noise coming over so that we will have fake coincidences or wrong coincidences, and this will show up as a background noise. And so now to quantify the SNR of the system, we can use what is called the coincidence to accidental ratio, which is basically a measure of how visible the center peak is. And this is an important metric because it's directly related to the quantum bit error rate, which dictates if we are allowed or not to establish a quantum communication link. And so the main way that noise is mitigated in quantum systems actually is the same way that we would mitigate noise in classical systems. In particular, we want to attenuate unwanted light either in the time or in the frequency domain, so we can use temporal gating or bandpass filtering. But this usually leads to a high degree of losses because we have to put in these systems that are lossy, and also requires to have a precise knowledge about the time and frequency properties of our signal. And so there's been some effort to devise new ways to deal with noise in quantum systems, but they either impose some requirements on the quantum state themselves or on the network. And so we would like to have a universal denoising scheme that doesn't impose strict requirements on the system. And for this, we propose to use temporal imaging. So the main idea behind this can be just interpreted by how a lens works. So for example, let's take that we have this weak cat image that is in the far field such that its light rays are propagating parallel to each other. Well, then when they arrive on this lens, they will coherently all acquire a tilt. And then after being tilted, they'll go through the diffractive propagation, which will leave the focus to the focusing onto a singular point. Now, if we consider that this image is drenched in noise, this noise is pointing in random direction. And so when it gets to the lens, it will not acquire the quadratic wavefront that it needs to be focused. And so we can see that there's kind of an increase in the signal to noise ratio of our image, except that now it's much smaller. So our proposal differs in the sense that now we use an array of lenses, and this relieves some of the demands in the resolution that we have in order to reconstruct the image. And it also solves the problem that it's very difficult to construct a very large lens. And so once that we have this array of points, we can do a peak selection. So we take only the points where we have focused the image that we want. And now we can see that we have a significant improvement in the signal to noise ratio of our image. So we wondered, how can we, instead of applying this to an image, apply this to the joint temporal distribution of entangled photon pairs? And as you might have guessed, the answer is to use a temporal imaging system. And now, since this electro-optic phase modulator and dispersion is operating on both photons at the same time, we can imagine this as being a two-dimensional phase mask that we are applying on the temporal distribution of our joint photons. And so this leads to the redistribution of our signals into peaks that we can do the post-selection on. And so in order to have a high amount of denoising, we want to have a high compression factor, which we define here as the ratio of the peak separation, so TQ divided by TS. So we want to have a high focusing to allow for a lot of noise mitigation, because now this allows us to remove all the noise that is placed in between these peaks. And so we can go in more technical details if you want later, but actually the way that we implement this is not by using a lens per se, but we're using something that is called a Talbot array illuminator that's phases derived from the Talbot effect that can basically be understood as Fresnel lenses that are used in White Houses that wrap the phase to a 2π phase excursion. So you can have the same effect of a very deep lens by only restricting your phase modulation to a 2π phase excursion. And so this is the experimental setup that we use to demonstrate this. We have a pulse laser that we generate by carving a CW laser using an intensity modulator. We then send these pulses to our microring resonator, and then we send this to our notch filter again to separate the pump from the photons. We then inject noise using erbium-doped fiber amplifier, an EDFA that has no input. And then we combine them and we send them to our denoising module that are composed of the similar elements. And then finally, we can separate our different signal and idler photons in order to do the detection. So this is the result for the single photon distribution. Yep.
Might be very expensive, but because your system is not ideal, then you have some sort of phase rapidly. You just want to restrict your 725. Is that a problem?
Yeah, so actually it would be, so when you have an electro-optic phase modulator, it has what is called a V-pi, which is the voltage that you have to put. And usually there would be maybe around 2-3 volts. And the maximum voltage that you could put is maybe around 10 volts. So if you look at making a quadratic lens, you can really do about 3 pi phase modulation. So to overcome this, we limit ourselves to 2 pi and we do the modulation much faster. And so this allows to, and so since it like everything, all the phases up to 2 pi are equivalent to each other, we can have this very deep lens that instead of implementing it, which requires maybe hundreds of pi of phase excursion, we use only 2 pi, but we have a requirement that this phase is now varying much rapidly. So this is the requirement. You have the benefit of low phase excursion at the cost of high bandwidth. So these are the results, and you can see here that we have a very low SNR because you can see here that the signal of interest is this dark red part, and the noise background is it's much larger. It dominates significantly over it. So now we take this this photon and we send it through our denoising module, which here is designed to have a compression factor of 77, and this is what we measure at the output. You can see that because the noise is only 9 gigahertz, so this is some relatively narrow band noise, it actually does get refocused into these peaks. But our microring resonator has a resonance width of hundreds of megahertz. So it gets redistributed into these much narrower peaks. And so we're still able to do the post selection and see a significant enhancement in the SNR. So now if we look at both the signal and the idler, and we look at the correlations, we can see that the two-dimensional joint correlations are also redistributed into these peaks. And now this allows us to get rid of all the noise that we can see in between these peaks. And so we characterize this by the car, and we can see that we have nearly a 10-fold improvement in the car using our method. Here I'd like to stress that we are actually comparing the input to the output. So this also takes into account the insertion loss of our device. So now we wanted to go into more of an application scenario. So we did another quantum interference measurement similar to the one I showed before. And so again, we use a single interferometer to process both the signal and idler photons simultaneously. And after we separate them. And these are the experimental results. So you can see that if we look at the source, this is what's shown by the dark line. You can see that as we start to inject noise, we quickly fall below the threshold for band equality, really reaching a very low visibility of only 29% at the highest noise setting. On the other hand, if we look at their denoised output, we're able to maintain a high degree of visibility throughout, so that this would be an example of where we could establish some quantum communication link that would otherwise not be possible. So finally, we wanted to have the full complete measurement. So we went ahead and did the quantum state tomography measurement. And for this, we need to be able to process the signal and idler photons separately. And so we used a demultiplexer to separate the signal and the idler photons. And now we can individually set a phase on each of them. And these are the results that we obtained. You can see at the input that we have, you can see that without any noise injection, we have a high fidelity of above 0.9 in both cases for the input and our denoised output. Whereas if we look at the case where we have noise injection, our input quickly falls to a low fidelity of 0.62. And you can see that the real part of our density matrix now is heavily corrupted. But now if we look at the denoised output, we see that we're able to increase our fidelity to 0.86, showing that we're able to recover the entire state with higher fidelity. And so this work went into different directions. It was applied in a classical domain where we showed that we can process multiple data signal and improve their bit error rate. We implemented this using nonlinear optics and showed that we can process high-speed data signals. And we also showed how we can do the post-processing directly in the physical domain. So this avoids the requirement on the temporal resolution for the detection at the cost of putting the bandwidth requirement instead on the gating. But I would just like to give a quick show some quick results on noise mitigation of broadband signal through spectral processing. So what do I mean by spectral processing? Well, I showed how a lens can be used to focus an image. Well, we know that a lens can also be used to collimate an image. So for example, if we take this point source, we can see that it has k vectors pointing in all directions. And then we can use a lens to collimate it. What we're doing when we're collimating is we're effectively making all of these different rays point in the same direction. So we're focusing in the spectral domain. And so this is the concept that we want to use, but instead now for a time frequency signal. And so this is the experimental setup. We use a mode lock laser with a wave shaper to give it some shape. Again, here, this is a classical experiment, so there's no nonlinear parametric down conversion. And we drawn it with noise. And this goes through our spectral denoising module, and we can talk about it at the end if you have further questions. But the main difference is simply that we flip the operation between these two modules. So we first have so at the input, we would have our broadband pulse, and then it is dispersed by this grating. And then by doing the phase modulation, we see that it's instead the spectral domain representation of a waveform that's refocused into a series of peaks, a bit like a frequency cone. And then we detect it using an optical spectrum analyzer. And so these are the results. Here we have our weak input waveform that's normalized to a power of 1. And this noise background here is significantly stronger, having a power of about 30. So when we put both of them together, you can see that we are absolutely unable to see our signal. And here I'd like to stress that the noise that we're putting is within the same band as our signal. So we cannot use a bandpass filter because we're not able to see where our signal is in the spectral domain. And in fact, you can see here a signal is about 15 dB lower than our spectrum for a given wavelength. And now by activating our phase modulator, we see that we have the formation of this frequency cone structure that closely follows the profile of our input pulse. And so here we're using coherent energy redistribution to process the frequency domain representation of a waveform. Okay, so this brings me to the last section of this talk. Now we know that lenses are useful to compress or magnify an image, but lenses are also widely used to do a Fourier transform. And so here we'll show how we can use the time lens to do a spectrogram analysis of a signal. So if we have a temporal signal, we often have to do some kind of processing on it in order to extract some information of interest. Probably the most common transformation is to take the Fourier transform, and this will give us a distribution of the frequency component of our signal. However, there's an important question that it doesn't answer. When do these different frequency components arrive? So for this, we need what we call a spectrogram, which is a two-dimensional distribution such as this one that relates where the different frequency components arrive over time. And so the way that this is obtained is through the short-time Fourier transform, which I will illustrate using our example signal. So here I'm focusing into a short region of our signal. And the first step is to isolate this signal to a very short region using a windowing function. So we're basically multiplying this square pulse with our input waveform in order to isolate just a small segment of our signal. And then we can take the Fourier transform, which will give us the frequency components that are localized in this region. Now we can repeat this many, many times, which will give us a series of different Fourier transforms. And now we can simply plot them vertically one to another in order to reconstruct this two-dimensional distribution. And so this kind of technique to analyze signal was developed in the early 1900s for analyzing acoustic or slowly varying electric signals. But now there's a need to be able to have this kind of analysis in real time over some very large bandwidth for all these different range of fields. But the technology right now is just not able to keep up. So probably the most common way to do this is to use digital signal processing. And what this does is simply that you take your signal and you digitize it, and then you use a computer to take many Fourier transform and give you the spectrogram. This has no limitation on signal duration and has very high frequency resolution, but it has quite modest performance in terms of processing speed, instantaneous bandwidth, and time resolution. And then you can go to the opposite side of the spectrum and look at the techniques that are used for ultra-fast pulse characterization, such as FROG. They allow for extremely wideband analysis, but they're usually not real time, and they're quite limited in the maximum time duration of the signal that you can analyze. Especially if you want to be in signal stat acquisition, you need to have a pulse that is shorter than 100 picosecond if you want to analyze it. And so here we propose to use the time lens in order to do this operation, and I will show that it has some significant benefits for these different metrics. So the basic idea can be described through a CW to pulse conversion. So similarly to what I just showed before, we can take that we have this kind of narrowband signal here, and when it goes through our electro-optic phase modulator, the time lenses will lead to chirps as shown here. And then when we go through the linearly chirped fiber rag grating, this will lead the different frequency component to travel at different speeds, which will lead to a focusing. And this is exactly what we exploited for the noise mitigation demonstration. But now consider that we have a second frequency component in our signal, spaced a frequency delta nu naught away from the first one. Well, the chirp will have a similar effect on this frequency component, but now there's an important difference when it goes through a dispersive medium. In particular, because of the different central frequency, this will lead to a focusing at a different temporal location. And the spacing between our two pulses directly depends on the frequency separation. So if we know what was the amount of dispersion by which our signal propagated, we are able to reconstruct the frequency separation. And since this analysis is done for each lens, we're able to dynamically analyze how the spectrum is changing. So in other words, we have the time-mapped spectrogram. So this is the experiment that we showed for this. Again, this is all in the classical domain. So first, we want to generate a signal that has some interesting time frequency feature that we want to analyze. And so we take our laser, filter it to a bandwidth of 56.4 gigahertz. Then we split it into two paths with two different gratings, and we recombine it. And now this has a signal that has variation both time and frequency. We then analyze it using our time-lens spectrogram, which is designed to have a time resolution of 200 picoseconds compared to DSP, which had hundreds of nanoseconds of resolution, a frequency resolution of 5 gig, which is worse than DSP, but that's the cost for operating fast. And it has a broad bandwidth of 56.4 gigahertz. So this is what we measure at the output. We can see that we have a series of peaks. And if we zoom in here, I'm comparing how they are drifting with respect to our time-lens signal. And so we can see that because they're drifting, that means that we have some changing spectral content in our signal. Now we can take each of these sections and plot them vertically next to another. And now we have this time frequency representation, the spectrum. And now from this, we can analyze various properties of our signal. In particular, we can see that we're able to recover the amount of dispersion by which our pulses traveled with high fidelity. All right, so this project we also took into a wide range, into many directions. We used it to analyze very broadband signals extending over a long duration. We used a phase recovery algorithm to reconstruct the amplitude of our phase of our signals. And we also use them to analyze QAM data signal without using a local oscillator. So usually the way that these signals are analyzed is by combining a local oscillator with a signal to do coherent detection. And so we're able to avoid the local oscillator using this technique. We also recently showed how this can be applied in the quantum domain to show how the spectral correlations are evolving through time. And we can also, the similar way that I showed how noise mitigation could be done by spectral processing, well, this technique can also be done in the spectral domain, where now we are effectively looking at the time domain variation of each spectral bin. And so this allows for very broadband analysis. But I would just like to finish with an interesting functionality that we developed for time frequency manipulation. So here we're considering the following problem. Imagine that I give you a signal that has two chirps. So it has one chirp that varies from a slow frequency getting faster and faster. And at the same time, we have a downward chirp. So a component that is varying fast and going slow and slow and slower. And now I'm asking you, are you able to separate these two chirps and to just give me one of them? Well, if you look at spectral filtering, this won't work because this is gonna remove both chirps at the same time in a given spectral region. You can't use temporal phase modulation either because this will just remove a full chunk. So how can we do this? Well, we came up with a way to do this using our time frequency spectrogram, as I'll show shortly. Again, the main way that this is usually done is by using digital processing. And you can see again that we have some very limited performance in terms of speed. So the idea here is that we have our input signal. We then go through our timeline spectrogram that I showed before. And now in the time domain, we have both the time and frequency information that is dynamically varying. So we can directly modulate it and process it in the time domain in order to affect its time frequency properties. And now, because these are all only phase manipulations, they can be simply counteracted by putting the opposite phase transformation on them. So here we can have the dispersion opposite to the first one, and this will reconstruct our signal, and now we will be able to have a signal that is composed of a single chirp. So again, the way that this is done, we have our input signal that we send to our spectrogram, and so now we have these series of peaks in the time domain corresponding to the frequency components of our signal. We then use an intensity modulator that is programmed to select just a certain portion of our signal. So for example, here we're getting rid of this blue component. And now we take the signal and we send it through a dispersion that is matched and opposite to our first one, and this will reconstruct our signal, but now you can see that we were able to remove one of these components. So this is the setup that was used for this experiment. I will go piece by piece. So first, we generate a signal that is composed of these double chirps. So we have one chirp that goes from 670 megahertz to 46 gigahertz, and another one that goes the other way. And so this is the signal measured in the time domain. And we can do a numerical STFT, a numerical short-time Fourier transform, to show us that we indeed have these two chirps here. Now we take this and we send it through our time map spectrogram system that I showed earlier. And now this gives us a series of peaks. And now if we take each of these bin and plot them vertically next to another, this gives us our time map spectrogram. Now we take the time map spectrogram and we send it to our intensity modulation scheme. And we're able to just select one of these two pulses. So for example, here we're removing the S2 chirp. And so you can see what this means in the timeline spectrogram here. And at the output of our modulator, we've seen that we were able to remove one of these two components. So now, however, we are still left with a bunch of peaks in the time domain. And so we want to compensate this. So to do this, we now go through the dispersive medium that has opposite sign to the first one. And now we are left with a continuously varying signal. And if we take the short-time Fourier transform, we see that we're indeed left with the single chirp that we were looking for. All right, well, on that, I would like to conclude my talk. I presented principle behind space-time duality for, as well as for imaging system and manipulating time frequency signals. I showed how this could be extended to entangled photons. I demonstrated how we can combine both temporal and spectral phase manipulation to do imaging system that allows for noise mitigation in quantum systems, and how this can be adapted for dynamic spectral analysis. So just very quickly, I'd like to mention that now I'm on a new adventure with Prof. Lukas Kostowski and Jeff Young, and I'm investigating ways to generate large photon states. So there's been demonstration of 4-photon graph state in the path degree of freedom, and there's been demonstration of 2-photon graph state using controlled phase gates in the time frequency degree of freedom. And here I'm curious to look at ways to combine both of these strategies to have large photon states that are entangled into the time frequency degree of freedom. So this should be more scalable than looking just at the path degree of freedom. And finally, you've noticed that throughout all my application, I've been combining on temporal and spectral phase modulation. There's a lot of smart people at UBC and elsewhere that are figuring out the problem of the temporal phase modulation. So I will be focusing on designing integrated dispersive lines where the main challenge is to create a large delay between frequency components on a small form factor. And so with that, I would like to thank and acknowledge the work of many people that contributed here. I would like to acknowledge Prof. Jose Asanya, who was the PI in most of this work, Majid Godzari, who led the work on analog post-selection, Connor Rowe, who worked a lot on the time frequency stuff and partially led the QAM decoding. I would like to thank Emmanuel Fernandez, who led the work on nonlinear Fourier mixing spectrogram, Xin-Yi Chu, who led the work on the time frequency manipulation, Kyunwon Lim, who led the work on the sonogram, as well as Dr. Nicola Monto behind here, who worked with me on the quantum denoising and the spectrogram work. So with that, I would like to thank you for your attention.